Can you see, Tushar?
Yeah. So I guess you can put it on the scope, or you can just put upside down. Just
One
don't touch the pin.
minute. I think it will take time to just.
Yeah, no issue. Just be careful. The board is highly sensitive, so you make sure that you do not touch any of the pin on that microcontroller. Okay, you can turn it upside down. There's no issue with that.
Tushar sir, again you can instruct the 39 and 40 pin, whatever you said is the connection.
Yeah. He will
So
show
it may be
you.
recorded. Okay.
Yeah, he will show you, Shankar. Once he'll show, now it will be clear. It's just you have to just insert your pin into that black box which is provided over there, and pin numbers are actually written on that particular thing. Okay,
So
so
now, okay. So this is board. Okay. Can you see it?
yeah, I can see it. You just turn it little bit so that people can see. Just turn.
Okay.
Yeah, like that. Yeah, like that. So you put it up little bit, so that we can see that pin. So everybody can see. He has inserted one male connector into that J440 block. Okay, so that's it. It will be connected to your oscillos. I mean, it will be connected to your scope one probe. Okay, and other probe of scope will be connected to ground as well. So
Huh.
you also insert one cable into the ground pin. Okay, ground pin will be there into that. I guess it's there just beside J4 20 pin is the ground pin. Okay,
So I need three male to male pins, right?
yeah, three male to male pins you need. Yeah, exactly. So you can put one in J440, one in J439, and another one in J220. That is
One,
ground connection.
1 minute, 1 minute.
Yeah,
Okay, so first two pins from J to J4. But Tushar,
yeah.
why in the back side pin number is like P00 and P01?
Uh, P00P01. It's showing that your pin number is incrementing from zero to other pins. Okay, it's actually J440 only. Okay,
Okay.
so
So
from 40, then
backside number is different and front side number is different. That's why I asked.
no, actually, if you turn the board now, then you will
Mm-hmm.
see that J4 pin number 39 is nothing but that P01 pin. Okay,
Okay, yeah. That I understood.
yeah, yeah. So
So,
it's like
okay. So one pin right now, one pin is in 40, one pin is in 39, and then
exactly
I have to put next pin where?
J220, just beside that 40. There's one ground written over there on that board.
Yeah,
You can
ground
see.
written over there.
Yeah. You can just put your one pin into that. Okay.
Okay, finished.
Okay. Now you can connect one probe to J4. I mean J440 and one to ground. Okay. That ground probe connection is there now. You can connect it to ground, and main you can connect to J440.
One.
Okay.
Yeah.
Okay. So I guess everybody understood the connections, right?
So one probe to
J440.
1 minute.
Board is only partially visible. Yeah, you don't have to look at the board, Muthu. It's not necessary to see the board. Okay, right now we are interested in PWM signals. So I told before how to actually connect it to board. Okay, Zoom will show once again in
So
the
there are
webcam.
in the J4. Can you see it? Can you see this?
Yeah, I can see. You can explain now, Zoom.
In the J4, first two pins like P01 and P02. Here J4 is written. So I have connected two pins at first, two male to male pins. First at pin number 40 and 39.
Yeah, and
And
one
one
pin to the ground.
ground. Okay.
Yeah, so ground is just beside that J440. Okay, now we'll connect our scope and we'll connect our main pin to the J440 and other pin to the ground. I mean probe I'm talking about. Okay, so that you can see EPWM1A signal which is J440 and EPWM1B signal is J439. Okay, so we'll see one by one. So first we'll look how does EPWM1A signal exactly looks like after running the PWM code. Okay, then I will explain in little bit why it is like that. Then you will understand more better.
Okay, develop.
Is it connected? So
Yeah, almost 1 minute. And then,
okay, it's
okay,
connected, na?
so there
Okay,
are
then
two. Okay, first,
yeah, yeah.
this there
You
are, it will go to a ground, right? This one.
yeah, the small one will go to ground. So with the pinch, okay, yeah, that one
And
will go to ground.
this one now.
Yeah, yeah, that will go to ground, and that will go to your main. Okay,
Okay, understood. So first one I need to connect to the G40, right?
J440. Okay, don't touch the pins. Okay, and please be careful that you're not short circuiting any wire. Okay, that wire should not touch each other. Once you just connect it and then you can rest. Okay, so make sure that the weight of that probe will not make fall for your microcontroller.
Yes.
So I guess you have connected ground now.
1 minute more. I haven't connected it.
Okay, okay. Take your time.
Is it okay?
Have
Yeah,
you
I have
connected it?
everything. Yeah.
Okay. What you do now, so you just present your screen. Okay, your screen is on, right?
Yeah.
Yeah. So can you show us the code of EPWM up down counter? Have you imported it from C2000 where?
No, not right now.
Okay, okay, okay. What you do now, you present your screen and you open that C2000 where. Okay, you are already presenting your screen. You open that. Okay,
Okay.
what you do now, you go to Resource Explorer.
1 minute now.
Yeah.
Resource Explorer, then.
Then you just click Resource Explorer once. Yeah, you go down from here.
Okay,
Okay,
then
you see EPWM, that is already on. So, okay, you just see EPWM code, EPWM up down code. Come down, come down. It starts with E initial. So it will be after D. Yeah, you can see over there. So
this one.
EPWM, yeah, yeah, yeah. You import that. Okay, I guess it is imported. Okay, you go to the Project Explorer and build it.
This one, right?
Yeah, the up down counter.c, it's written over there.
Yeah,
Yeah,
directly.
you just no, no. You open the main file first. Open
Okay,
the
yeah.
main file. Yeah, .c file, first file,
Acha,
first
first.
file. Yeah, yeah, first one is the main one. So you run this, build this. Okay, you just build it. So it's building the code, and then you can debug it with the help of that key just below the navigate button.
Okay.
Okay, just below the navigate button, you have a debug key. Yeah.
CPU one
Okay.
or CPU two?
You
Anyone?
can select. Yeah, you can select one only. Okay, it's a code on one. So by inherently it will take CPU one. Okay. You just click OK. Okay, and let it get dumped onto your hardware. Yeah, you can click the resume button now, which is the green button. Yeah, and you can show your scope. So
Yeah, I show it.
webcam. Yeah, you just click auto scale once.
Yeah.
Can you check if pins are corrected properly?
Okay.
Yeah, you just check once it is connected properly or not. Okay. I guess many glitches
I
are
think
there
so.
in the.
Some pins are loose contact because of that. It is a fluctuation. That's what.
Yeah, it is fluctuating like that. So
Hmm.
just connect one pin only, J440 and ground. Okay, I think yeah, it is visible now. Yeah,
Okay.
you see the horizontal scale button over there. So can you see the horizontal scale button of your scope?
1 minute.
Yeah, you just zoom it a little bit with the horizontal screen button. Okay, I think that will be middle button. Yeah, yeah, yeah. Okay,
Intensity adjust. Wait.
yeah. You
Move.
see the middle button, maybe that middle button.
Horizontal, Tushar. This is horizontal,
Okay,
and this is vertical. All these things vertical. Okay, I
okay, okay.
can.
Horizontal, you just little bit. You show us the frequency of that PWM. Yeah, yeah. Yeah, this side, this side. Yeah, okay, fine, fine.
Okay.
Little bit zoom once again, once again. So what you do now, you make little bit more. I mean, I want to see more screen of it. Okay,
Okay.
okay. Do one more thing. You just turn that knob into left direction. Okay, one more time. I'm asking you to reduce the scale once more. Yeah, yeah, more. Yeah, more like that. Yeah, fine, fine, fine.
Okay.
Yeah, fine. So you can see from here, okay, your PWM duty is changing. Okay, even though your frequency is constant, your PWM duty is changing. So it is your EPWM 1A signal. Similarly, there will be EPWM 1B signal. Okay, so can you see the frequency of this? Is it possible for you, as you are new as a user to the scope? Can you just measure the time period? That what is the time period for that?
I'm using
Particular?
it first time. I don't know anything. You just tell me. I will do it. I think this is
Okay,
the Swiss sent means this is screen touch. So
okay,
it will.
okay, okay. Can you see what is the time scale per division?
Okay, wait.
That
Major, then advance. Can I measure?
any measure button is there, you can measure frequency. Okay,
Yes. Percent of amplitude. Uh, Mean. I can measure mean. Okay, frequency. Got it.
okay, frequency is there. No, okay, fine. You just
Yeah.
click
So
on
now
frequency.
we are 12.49 kilohertz.
Yeah, it's a 12.5 kilohertz. So
Yeah.
everyone now, can you open the code?
Sorry. Can you?
Open the code Composer Studio. Yeah,
Can you see this 12.49 here?
we can't see it, but it's fine. We trust you. You
Okay.
just
No,
you
actually,
just
wait.
open.
I will make
Okay, you
you.
just
You
open
see.
CC Studio.
See 12 point.
Yeah, so it's fine. It's
Okay.
fine. You just show the PWM signals. That's what we wanted to show, that it's varying duty. Okay, you can see that duty is varying. Okay, can you go back once and show the PWM signal again? As
Okay.
this is just the options we are seeing. Into your webcam only. Yeah. Can you go back? Can you show us the signal? Is there any back or escape button?
Yes. Can you see?
Yeah, yeah. You just yeah, it's fine. Now it's visible. Okay, so you can see everyone that your PWM duty is changing over here in this particular program. So I'll explain you why this duty is particularly changing here. Okay, this is happening because we are changing the comparator value. Okay, now why we are changing the comparator value? Since it is an inbuilt algorithm, in that algorithm comparator value is assigned to be changed from minimum to maximum value. Okay, so that minimum to maximum, can you open the code? So
Um, yeah.
yeah, you just stop presenting for a while. I will start presenting. Okay,
Okay.
I want to explain the code. So is my screen visible to everyone?
Tushar, can I directly unplug that thing or what?
No, you just let it get connected. Okay, we have to do some experiments. So you
Okay,
just let it be like that. Okay, for some time. Is it
okay.
possible to keep it like that?
Yeah, it is possible.
Yeah, yeah. Just hold on for a minute. Okay, we have to do some changes so that I want to see the change in frequency. I want to show them. I want to show them how duty you can make constant as well. Okay.
Okay, okay.
Yeah, fine. Shankar, are you here?
Yes, sir.
Okay, so in this code, Shankar, your duty is varying. Okay, so
Yes.
if you understand this code, you can as well make your frequency vary. Okay, so you have to
Okay.
understand it. Okay, and you can write your own code that how to change frequency of that particular signal. Okay, so
Okay.
if you have any issues in between, you can ask me. Okay,
Okay.
yeah. So everybody can see my screen, right?
Yes, sir.
So okay, so I'm starting from here. So this is the header file which is there in order to include all the declaration of your predefined function, as I said yesterday. So here we are defining some variables. So these are the predefined variables. Okay, EPWM1 timer TBPRD, and we know TBPRD is a time-based period register which is there in order to put your value for time-based counter, which is a 16-bit, and thus value for this will be 0 to 2 to the power 16. So you can put any number, integer number in between this 0 to 2 to the power 16 in TBPRD. Since our TBPRD value is 2000, as we saw that I guess I hope that thing is here. Okay, it's not here. So I'll just write one more time what I said in previous session. What I said in previous session, if you guys remember, uh, our EPWM clock, our EPWM clock was system clock divided by 2, and system clock was at 200 megahertz, so our EPWM clock was equal to 100 megahertz. This is for type 4 EPWM module which we are studying. Then we had a time-based submodule, if you remember, and our time-based clock was actually a pre-scaled version of your EPWM clock, and it was clock division into HSP clock division, which is a I'll reduce its size so it's very less. Okay, so your time-based clock was something like this. So you know your EPWM clock is at 100 megahertz, and we saw previously that our clock division by reset on default it is set to 1, and HSP clock division by default it is set to 2 if you are putting TB resistors like that. Okay, so why it is like this, as I've said before as well, from the technical reference manual. Okay, I think I don't need to show it again as my all tabs are also closed. So it was total 50 megahertz. Now, as we know, this is 50 megahertz. So our time for TB clock. Now, what I'm talking about is this particular time, T clock shown over here. Okay, so that's right. Yeah. So from here, T for TB clock will be 1 by 50 megahertz, as we saw before, and which is equal to 20 nanoseconds. Now, our PWM frequency we saw EPWM. First we calculate the time period, and for up down counter it was twice because we are tracing TBPRD twice. So we can say 2 into TBPRD. Why it is like that I have explained before. For up counter it will be 1 over here instead of 2, and into T for TB clock. So if you do this, what you will get is 2 into your TBPRD is 2000. In this case, you can see from my code, it is set to 2000. Okay, so if I'm setting at 2000 and time for TB clock, I'm setting at 20 nanoseconds. Okay, so if I calculate this, I can get my FPWM equal to 1 by TPWM. So this will be total 2248. 80000 nano. If I calculate this, my frequency, I'll get it to be 12.5 kilohertz. Okay, so this is the frequency of PWM. This is how you can calculate it. Okay, so that's why since our TBPRD is 2000, we are getting frequency as 12.5 kilohertz. Okay, now correct me if I'm wrong. Is it fine? Is it everybody understood how I have got this value?
Yes, sir.
Okay, so I guess now we are good to go with rest of the portion. So we can see here our maximum comparator A value is 1950, minimum comparator A value is 50, maximum comparator B value B is 1950, and minimum comparator B value is 50. It means your comparator is varying from certain minimum to maximum value. Okay, and that's why my duty is changing. Now how exactly I'm changing this comparator is that I'm making the use of interrupt that we saw. Whenever any event occurs, we can trigger an interrupt, and with the help of that interrupt, I can vary my PWMs. I can vary my comparators. Okay, so before that, I would like to explain you a little bit. This is a portion structure. It's written in C. Okay, so in this structure is basically a set of variables. So you can use a pointer in a structure as well. So we have declared certain set of variables which are unsigned integer of 16-bit, like comparator direction, timer interrupt count, maximum comparator A minimum, and these values. Okay, so these variables we have assigned for our operation over here, and we have assigned a pointer known as EPWM register handle. Okay, so this pointer will actually track the address of your all the EPWM registers. Okay, so it's a volatile type of structure. Okay, after that you can see that structure is named as EPWM info. Okay, so in this EPWM info, with this particular structure name, I can access each and every information of whatever variables I have assigned into this structure. Okay, now from here to EPWM info, I have assigned three more things. One is EPWM1 info, 2 info, and 3 info. Since I'm simulating three PWMs into this case, I have taken it as three variables. Okay, so these are the function prototypes. So we are using three PWMs. So we have three functions over here: PWM1 function, PWM2, and PWM3. So these are the declaration of your functions that you are going to use. Then you have three interrupt function. Three interrupt you are generating from PWM. So you have declaration of three PWM interrupt ISR. Okay, so this is called as a declaration of your function that you are going to use. Okay, so you have declared this function outside your main, means these are the global functions, that any of one of the if and the variables over we have defined over here are all global variables. It means that any of the functions in your code can have access to any of these variables. Okay, so let's start from mains. So as we saw previously into our main code, that we have first API, which is initialization of system control, which means that we are initializing all the peripheral clocks and as well as main clock of your microcontroller. Next one is your GPIO initialization. Since it is not required here, we have put it off. This is not required because in API of EPWM.C, we have already defined and we have already assigned GPA mux GPIO 0 as 1. Whenever we are deciding this as GPIO 0 as 1 into this particular mux, it means it is operating as EPWM 1A. Similarly, GPIO 1, which is J439, we have assigned it as EPWM 1B by putting 1 over here. If it will be 0, it will be acting as a general purpose input output bit. Okay, so that is already there into this EPWM.C. API which we are going to call. Next thing is you have a peripheral clock enable here. So this is a peripheral clock. P clock means peripheral clock, and it is in control register 2. Okay, so this peripheral clock control register 2, its EPWM bit, we are switching it on. It means we are switching the on clock on for EPWM 1. As I told you, every module works on its own clock. So for that, you need to initialize or enable the clocks of PWMs that you are using. So you are using PWM 1, 2, and 3. So you have enabled the clock of PWM 1, PWM 2, and PWM 3 into your example. Okay. After that, you have initialized EPWM 1 GPIO, means GPIO 1 you have set as EPWM 1 pin. Then you have EPWM 2, and then you have EPWM 3. So into this function, you can see we have assigned a GPIO as EPWM. So this is the same API which I have shown you before. So in this API, we have set GPIO pin as a EPWM. Okay. So these are the pull up and pull down resistors. Okay. They have disabled the pull up onto this particular thing. Okay. We are not concerned about that thing. We are just concerned about this thing. Okay. So this is how you initialize PWM, which are predefined functions. After that, you disable all the interrupts as we saw as a part of procedure that we need to clear all the interrupts. Then we have initialization of Pi control, that is peripheral interrupt expansion control module. And we are initializing that Pi control module, which is required in order to generate a particular interrupt. Then we have core interrupt, that is interrupt enable register and interrupt flag register, and we have cleared these registers as well. Next, we have a pi vector table, initialization of pi vector table. So this procedure is similar as I explained previously. We are initializing pi vector table as well. After that, we want to trigger 3 interrupts, that is EPWM1 interrupt, EPWM2 interrupt, EPWM3 interrupt, and it has to call the interrupt service routine after creating this interrupt. So it is calling this EPWM1 ISR, which is a function which I have declared before. You can see here EPWM1 ISR is a function, EPWM2 ISR is a function, EPWM3 ISR is a function. So declaration of these functions are there. So I have called this 3 function with these 3 particular EALLOW protected instructions over here. So this is from pi vector table that I'm seeing EPWM1 and 2 interrupt and 3 interrupt. Now this instruction I'll explain a little bit later in 2 minutes. Okay. So this is group 3 interrupt. How do I know it is group 3 interrupt? I have to look into again my interrupt table. So as I said previously many times, that group 3 interrupts belongs to PWM group, and from here you can see group 3 and subgroup 1 will be PWM1, group 3 and subgroup 2 will be PWM2, group 3 and subgroup 3 will be PWM3. So we have to initialize group 3 and subgroup 1, 2 and 3 for PWM 1, 2, 3. So we can see here main group is 3 and subgroup is 1, 2 and 3. So we are calling pi resistor. Just hold on a minute. Yeah, I'm sorry for the interrupt. So you can see from here that we are enabling core group 3, which is M interrupt 3. It is a enable switch, and this is logical OR operator as I said to you, and EM is used for enabling. So after clearing, we enable all the interrupts, and then this is pi block from which we are setting the interrupts. You understood this very well, I guess, how to you write this instruction, So if you know how to trigger one interrupt, you can write it for another interrupts as well. So subgroup 1, 2, 3, EPWM 1, 2, 3 interrupt we are triggering. And then these are the global switches of core logic in order to turn your interrupt on. As we saw, the logic goes through IER, IFR, and then global switch. Okay, so this was related to interrupt. Then you can see from here that you are calling these 3 functions, which is initializing EPWM 1, 2, and 3 functions. Okay, these are main PWM functions that you're calling, not your ISR. Okay, your ISR call is from here, from this EALLOW protected register. Okay, so we are calling ISR functions from here, and main functions in which we are writing code like PWM 1, 2 and 3 example in which we are writing how to generate PWM, we are calling those functions from these three. Okay. Then this instruction, which is indicating TB clock synchronization, it is there in order to synchronize all your time-based clock. Time-based clock in the sense, EPWM clock, as we saw, I can show you the presentation. So we saw from here that our time-based clock, okay, every module, EPWM module, has this time-based module. So every time-based module needs to synchronize with another EPWM module's time-based module. So in order to synchronize all the time-based submodules of all EPWM modules, you need to put that particular instruction. Okay, and that instruction tells you that if you first clear the bit, that is time-based clock synchronization, it means TB clock synchronization, means time-based clock synchronization, you have to set it to 0, and then at the same time you have to set it to 1. So you are clearing it first and then you are setting it on. So you are setting TB clock synchronization bit as 0 and then 1. So with this particular instruction, all the three PWMs module will get connected. So if you want to connect EPWM3 with EPWM4, okay, then you have to go for certain other thing that I'll tell you. Okay, first, all the three PWMs module, since they are connected in a row as we saw before as well in the construction diagram of PWMs, I can show you. So we saw from this particular thing that EPWM 1, 2, and 3, these are connected together. Okay, so this EPWM 1, 2, and 3, anybody wants to say something? Okay, page number 1713. Yeah, thank you. So from this we saw that this particular PWMs 1, 2, 3 are connected together. Okay, then you have 4, 5, 6, 7, 8, 9. So this PWMs, three PWMs will be connected together. So in order to synchronize the time-based clock of that particular EPWM modules ranging from 1 to 3, you have to first clear it and then you have to set it. Okay, so this is how you set and synchronize all the PWMs module specifically from 1 to 3. Okay, later you can see you have enabled this group 3. I think I have explained this. So from here, what is exactly happening is when you are running this particular algorithm, you are setting your TBPRD value to EPWM time-based period. We have not assigned any phase shift as of now, so we'll see about that. So this is comparator A, comparator B, which is set at minimum and maximum values. Then we have assigned it as a up-down counter mode, as we saw. Phase shift we have disabled. HSP clock division we are well aware of. These instructions should be as it is. So we saw that compare A count we are setting it to be on, and compare down D count we are setting it clear. It means your action qualifier will make your pulse on when comparator A will touch the upside portion of time-based counter, and it will clear the pulse when comparator portion will touch the downside of the counter. Similarly, for EPWM B, this instruction are there for comparator B as well. Now what is happening is, this is a ET selection resistor, which is known as interrupt selection resistor. So this interrupt selection event trigger, sorry, my mistake. This is event trigger selection resistor. So we saw one event trigger submodule was there, right? When we were studying this PWM, we saw this event trigger submodule was there. Okay. So this event trigger submodule is able to generate EPWM interrupt. You can see from here. Okay. So what we are doing is, this event trigger submodule, we are generating an interrupt. On what instant we are generating an interrupt? Whenever a counter start counting from 0. So whenever counter will come back to 0, if it is traveling from 0 to 2000, then 2000 to 0. So at every 0 instant, it will cause an particular interrupt. This is for interrupt enable. En means interrupt enable. We are putting it 1. Then you have a interrupt period. Interrupt period means when you have to generate an interrupt, you have to generate an interrupt on third event. It means when counter is at 0, then after 3 triangles of repetition, you are again, whenever counter will be 0, again at that point of time your interrupt will be generated. So you can say thrice of your PWM, that is thrice of your PWM timing. Okay, that will be the time to generate an interrupt. You can calculate as well. Okay, your timing for TBPRD, I guess it is time-based clock is I guess 2 into 2000 into 20 nanosecond. So thrice of that, okay, thrice of that time, after that time, this particular interrupt will trigger. That's what I mean to say. So this is a interrupt selection resistor which is triggered with the use of event trigger. Now whenever we are putting this on and we are triggering the interrupt, what is happening is after arrival of your interrupt, okay, immediately your code will jump to ISR loop. So ISR loop, it will execute. So what I have written into this ISR loop, let's say PWM1 is generating, and whenever counter is starting from 0 to 0, it has generated an interrupt. And after third event again, it is generating an interrupt after 3 triangles. So first interrupt when EPWM1 ISR is running, what we are doing is we are updating the compare value with the help of EPWM1 info structure pointer. So we can see here, I have assigned a structure pointer over here, okay, as EPWM1 info. So with this EPWM1 info, okay, what I'm doing is I'm calling that particular block which I have written into EPWM1 info, which is telling me that I'm updating the compare value. So I have to go to this particular EPWM info. Once this instruction is executed, similarly, what will happen after running of this instruction? My code will go to what? My code will go to yes, yeah. So from here you can see whenever I'm calling this update compare EPWM info, okay, so my code will immediately jumps to what block it will jump? It will jump to this particular block, which is a void update compare EPWM info. This function I have written. Okay, so this is update compare. As I told you, this is a keyword which I have used for the function, and I am handling it with the help of which pointer? EPWM info pointer, and I have assigned everything in a structure named as EPWM info structure. So what is happening exactly is once that particular interrupt has occurred, immediately it will go to ISR. From ISR, it will call this function, and this function will update the compare value. Now, how it will update the compare value? I have written, TI has written some condition over here, TI engineers, that if your EPWM interrupt count is between 0 to 10, like what's happening is whenever EPWM timer is causing any interrupt, okay, we have its count as well. So whenever that count is between 0 to 10, okay, your comparator direction will be up. Up in the sense it will rise from 0 to upward. And whenever we are putting comparator A direction down means it is going from down to below. So what we are saying here, the comparator value should be between maximum, should be less than maximum. So if it is less than maximum, your comparator will increase, comparator A plus plus. So why, if it is less than maximum, it will increase? Because it has to reach that maximum value of comparator, which is below TBPRD, which is 1950. If it is not the case, and my value is not less than comparator A, maximum value of comparator A, then my comparator has to come down. And when, till what point it will come down? Till it will take the minimum value of comparator. So you can see from here, you can see from this particular code that if your comparator value, okay, this particular arrow is also a pointer. Okay, this particular arrow is also a pointer. So EPWM1 info is pointing to EPWM register handle, which is a volatile structure in which all the comparator bits and all the maximum and minimum, whatever this unsigned integer you have defined, they are there. So this EPWM1 info pointer is handling or is calling this EPWM register handle structure. And in this structure, all these variables are put. That's why we are writing it like this. Okay. So next thing we can see from here that if your comparator value is less than your maximum value, your comparator will minus minus, it means it will decrement. So once it will start decrementing, okay, you have to once again change the condition. Similarly, you have to write the condition for comparator B as well. Okay, so what is happening here is your comparator is rising from 0 to maximum value, and once it has reached the maximum value, it is coming from that maximum value to minimum value. So how it is doing that? It is doing that with the help of this EPWM register handle and EPWM info pointer. And once ISR has happened, okay, once you can see every 10th interrupt, your comparator A and comparator B values will change. So you can control that as well. When your interrupt will change, okay, let's say I'm causing interrupt at a very less period of time, 2 into 2000 into 20 nanosecond. So 10 times of that particular interrupt count, I am changing the comparator value. Again, you put it 100 times, 1000 times, so my comparator will value will vary very slowly. Okay, so my duty will change very slowly. You can change this and you can as well see effect in your code. Okay, and if you want a fixed duty, you don't want interrupt to happen. If you don't want interrupt to happen, what you do is you just disable the interrupt. You just disable this core logic. If you just click on this and run the algorithm, what you will see is you will get a fixed duty PWM. Okay, so if you want to vary frequency, what you have to change is TBPRD, right? So if you want to, let's say if you want to vary frequency in closed loop, I will run the ISR loop in the same way. I will update the EPWM1 info, but this time I will not vary compare register. I will vary which register? Time-based period register if I want a variable frequency. Got it? So does anybody has any doubt? Till here
Last
what I have
statement,
explained.
last statement regarding variable frequency. Could you repeat it again?
I'm saying instead of varying your comparator values, which is from maximum to minimum, if you can vary your time-based period value, this value, time-based period value. Okay, if you're changing this, you will be able to change your frequency of PWM because your frequency of PWM is decided by which? TBPRD, na? So if you change TBPRD, you will be able to get your variable frequency PWM. Got it, Shankar?
Sir. But with this phase shift also means that phase shift you have
Yeah,
not
yeah,
enabled, that you have to
yeah, yeah,
make it.
yeah. Phase shift, what you have to do is see, you have a TBPHS here. Okay, so what you do is you put some value of phase shift over here. Like let's say you want to have 120 degree of phase shift. So for that, you need to put 1/3 of your TBPRD. So if your TBPRD is 2000, 1/3 of that will be 2000 divided by 3. So I guess it will be, 666 or something. So
66.66. Ah, yes,
uh,
666. Yes,
are you sure, Shankar?
6666.
Okay, I think. Okay, so this will be TBPHS, and you have to start your TB counter from TBPHS in order to give phase shift. Now, why it is like that? That I'll explain. So from here you can see that whenever I'm choosing my time-based counter to start at TBPHS, what will happen is my triangle will not reset to 0. Instead, it will not reset to 0. Instead, it will cause a reset at that point of time, whatever my TBPHS value is, and then my triangle will start counting. So in this way, we are able to achieve the phase shift into this particular module. So whenever you want to have a 120-degree phase shift, you have to choose 1/3 of your TBPRD value. Okay. So if you do that and you put your TB counter, okay, if you put your TB counter equal to your TBPHS, it means see, whenever you are giving phase shift, what you have to see is you have to assign one main module. Okay. So suppose this is my main module, and then phase shift is given with respect to the other modules, like one module is master and other modules are slave. So with respect to master, phase shift is assigned. Let's say I'm putting EPWM1 as 0 0, and I want EPWM2 to be phase shifted with EPWM1. What I'll do here is I'll assign that as a master, I'll assign this as a slave. So I'll put here 666. So in this way, my PWM2, which I'm generating, it will be phase shifted with my PWM1. Okay, it doesn't mean that I'm having this phase shift in particular PWM A and B. Okay, I'm having phase shift in EPWM1 and EPWM2. Okay, generally that is only required, like EPWM1A and 1B signals are there in order to give any two particular inverter switches. And when you want to have a phase shift for another leg, let's say, so what you can do is you can make the phase shift of this particular thing. And you also have to put here phase shift enable instead of disable. Okay. Here enable, okay, this will cause a phase shift. So it is like this. So this is how this particular example runs. Okay. And okay, till here, does anybody has any doubt?